All right, good morning. This is the first of our new series, Fireside Chat with the Experts. This is a new set of online presentations that we're going to give since with the 2020 coronavirus pandemic, we haven't been able to travel and give these presentations live. So we're going to be doing that from our homes now as we enjoy the sheltering home lockdown. So the first presentation or the first conversation we're going to have is going to be with, it's going to be a generic presentation we've given a couple of times that it will cover a lot of the background on X-ray inspection, some of the applications, and how X-ray is used in a daily basis in our industry to improve manufacturing. So today's presentation, as you can see here, we have quite an aggressive schedule. You know, we're going to cover quite a few topics. That's the reason why we split this conversation in two sessions. So we have today at 10 o'clock Pacific time, and next week, next Wednesday, we're going to have the second half of this presentation. We're going to keep on. We'll basically cover everything we missed. We didn't have a chance to cover today. And every Wednesday at 10 o'clock after that, we're going to have sessions of half an hour. We're going to keep it short and to the point so that we can fit in our busy days. Even though we're home, we are still quite busy. So I'm really happy to introduce you today to Dr. Glen Thomas, who's our VP of Technology. He is a guy who doesn't really need a lot of introductions. Be doing X-ray inspection for 20 plus years, even though he's super young. He's been in this since high school, right, Glen?
Pretty much.
And so today we're gonna, Glen's gonna give a presentation. Next Wednesday, I'm gonna cover some of the topics that we didn't cover today. And with that, you have the floor, Glen.
Thanks.
Let me give you control.
Yep.
So you can run the presentation yourself.
All right. How do we change slides?
Yeah, let me give it to you right now. I should be able to do it now.
What changes it? I guess we forgot to go over this earlier, didn't we?
I know. Well, you just let me know and I'll change the slide. Yeah.
So essentially, what we see here is we see a typical SMT line, right? We have the screen printer, SPI, pick and place, reflow, and AOI, as well as X-ray at the end. This would be the ideal setup. Some companies will make a choice whether they want to go with AOI or X-ray, and ideally you would want both. Most of the time they will choose between AOI and X-ray depending on their needs and how many problems they have. Typically with the X-ray and AOI, they both complement each other. They're not really inclusive one or the other, but most customers tend to pick one or the other. So, yeah, that's just the way that beast works. Okay, next slide. So essentially, you get a lot of defects with this manufacturing process for bottom components, bottom terminated components, and in solder joint integrity in general. Essentially, with X-ray for the SMT line, what we're looking for is solder joint integrity. We want to eliminate the excess solder. Which would be solder bridges and insufficient solder. And in that insufficient solder, you're looking at voiding, and you're looking at lack of solder joint integrity due to not having enough solder or solder paste, solder masks. So in these three areas, you have quite a few different defects that would fall under those three areas. Xray will actually find and excels in most of the areas, especially the insufficient solder. Okay, next slide. Again, we can look at misalignment, polarity, and missing components. And this is where AOI does a really great job. And Xray, it's just a matter of being a plus. You know, we can find misalignment, we can find polarity in most cases, and we can find missing components as well. But that's not the main focus for Xray. That would be more of a function of AOI. Okay, next slide. This is where AOI fails and Xray excels, is in the voiding, the bridging, the solder balls, excess solder, and insufficient solder. We can go over like gull wing components with insufficient solder later in the presentation, but Xray excels at these 5 key areas of SMT inspection. Next slide. Solder joint measurement data collected during Xray test and can be used statistically to analyze, identify manufacturing drifts, trends, and other process, right? So essentially what we're saying is we can use Xray, we can look at a solder joint, we can determine based on what characteristics the solder joint has, we can go back and we can pinpoint areas in the process that are most likely to cause that issue. So Xray will be able to give you an idea and monitor multiple processes and be able to show you drifts. So if you notice a drift in the process, you will use Xray to look at that and you can see a drift and you can actually go back and fix your process on the fly while you're still producing shippable product. One of the key problems that we see a lot of is people will use Xray only as a last resort and not necessarily manage their processes. So what they do is they use Xray as oh no, we have a problem and we can't ship product, right? Smart contract manufacturers and smart OEMs use the Xray to look at the process consistently so that they can see drifts, fix the drifts before they actually have a problem. Okay. Okay, basic principles of Xray. Xray, whether it's medical or industrial, all uses the same principle, right? We use an Xray source. Typically for small fine pitch components, we would use a 5-micron source or better. In some cases, if you're looking at magnification on very small components, you will need a much smaller focal spot than even the 5-micron. 5-micron focal spots, 3-micron focal spots are pretty much the standard in surface mount inspection and solder joint integrity these days. We always need a sensor. The old days sensor was film. We had some digital detectors back in the day that were pretty crude. We considered them digital, but they were actually just a phosphorescent screen with a digital or a CCD camera. And then we went to image intensifiers. They became the de facto standard for many years in industrial Xray and in surface mount technology. Now, flat panel detectors are the standard. It's rare that you'll find an Xray system with an image intensifier. And if it is using an image intensifier, it's going to be based on the application and the need rather than just a general imaging device. Xray sensors, the digital detectors excel, and there's a lot of reasons for that. The main reason is the digital gives us a better grayscale contrast, more spatial resolution, and we're not doing as much conversion. Image intensified systems have analog 256 grayscale, and then we pick that up with a camera, and there's a lot of inefficiencies. Then we've got to convert it analog to digital, so you have some more loss and inefficiencies. So digital detectors, flat panel detectors are going to be around. They're going to stay around. They're actually beneficial for companies when they do image processing. Okay, As far as, let's go back to one other slide, the back slide. As far as image processing, back in the day, image processing was pretty straightforward. We took an analog image, fed it out to a monitor, and we would look at it, and you would use a dry erase type marker or a crayon and draw on the actual monitor if you saw an issue. Right? You would we had 3 or 4 times frame averaging, and then we used last image hold. So you would do a last image hold, run down, you would circle the problem, run down and get the engineer and show him the problem. Then we went to image processing, which was kind of straightforward. It was about in the mid to late 80s. We had some image processing available. There were only really 3 companies that were building image processing computers at that time, and they were kind of archaic compared to what we can do with image processing today. But that also allowed us to use digital printers, or actually thermal printers at the time. So now we could save that image, right? And it became much more useful as time went on. Image processing today is actually the key to X-ray imaging for all types of components, because we have the ability to do some algorithms. We can automate the process, we can save data and use that data to monitor the process. So essentially, anybody can build an X-ray system with an X-ray source and a detector. The secret is really having a beneficial software to analyze and understand the information that you're getting from the X-ray machine. Next step. Why do we need X-ray? Back in the mid to late 80s, some bright engineer decided that bottom terminated components made a lot of sense. It made the board smaller, gave them a lot more interconnections. It just made sense to make a bottom terminated component. What they forgot about was what we'll talk about later, is the ability to inspect that and to actually verify that your process is working. So essentially, BGAs revolutionized the X-ray industry for X-ray imaging and surface mount technology. Up to that point, we built a few systems, but most X-ray systems at that point were to look at wire sweep, and we would look at components, and we would look at bare boards for interlayer registration. Didn't do a whole lot of X-ray for solder joint integrity, but the BGA changed that whole concept and actually built the industry that we see today. Next step. So if you take a look at a BGA, you've got a lot of balls underneath the solder joints. Those solder joints, there's a lot that can happen in there. You have solder paste applications, you have solder masks, you have the component itself, placement of the component. You have coplanarity issues with the board or with the component. So you have a lot of different issues that can happen on a BGA. In a perfect process, you put the BGA down, you apply some heat to it, the BGA self-aligns and everything goes well. But it's the process of placing a BGA sounds fairly straightforward, but it's actually quite a complex process that requires more or less perfect execution prior to soldering the BGA to the board. So if you can take a look at the X-ray image, you see that we see some solder balls. Essentially, those solder balls will give us a great indication as whether we have a fairly decent connection to the substrate, right? In this this image, you can see that we have some balls with no voiding. All the sizes of the balls are pretty standard and circular. So it's a fairly decent X-ray image of a BGA. And that's what most people strive for in the industry. Next one. QFNs. QFNs are interesting as well. Instead of the standard ball, we have a pad, and we need to mount or solder the components to that pad on the substrate. It's a different process. Some of the same processes as far as solder paste application, placing the component and your general placement of the product is pretty close to a BGA. One of the problems you have with QFNs is you have a lot less mass as far as the solder paste. So your profiles can get a little bit weird as far as heat. And they're close to impossible to inspect with AOI, same as a BGA. As far as the solder joint integrity on this image, those all look pretty decent. It's not too bad. And when I say decent, what you're looking for in this component versus a BGA is you're looking for the solder fillet, the rounds, darker areas around the circumference of each connection. And in this case, if you had a bad solder joint, you would literally see, instead of a nice rounded shape and a nice flow from light to dark, you would see just a straight line. It's easy to pick up, but those do look like pretty good solder joints. So the difference between BGA inspection and QFN inspection is essentially we're looking at solder fillets more so than the solder balls themselves. Okay, next. Right here, perfect example of a QFN. Essentially what we see is we see some voiding underneath the pads in a few places, but essentially we have a straight out open. There's no solder fillet at all. And by solder fillet, you can look at the connections and you can see the black blobs all along the bottom. And by inspecting a QFN, you've got a couple of voids in there, but for the most part, you have two opens, essentially. They're pretty easy to pick up and pretty straightforward. AOI would most likely could pick that up because it would be probably outside the component a bit on this component. But what AOI wouldn't be able to tell you is if you had solder flow up under the leads and you had a nice solder flow. But Xray will give you that indication that you have solder flow, because you could have a solder ball on the outside of that pad and outside of that pin and still not have solder flow or a real connectivity. And we can also see that all of those balls are somewhat round. When solder melts, it likes to puddle, and it will puddle in a circular fashion. When it's cold and it doesn't have a good solder connection, or the solder paste application is not actually working well, what you'll get is you'll get a lot of angular solder joints. And when in solder joints, angular is always bad. It means you have a cold solder joint and you have a lack of adhesion. So even with the with AOI, you might be able to pick that up. There's been all kinds of different concepts with visual imaging. A lot of silly scopes where they would try to look down under a BGA. And it just makes no sense. For a production environment, looking under each BGA is silly. It's just pure folly, because you can only see your 2 or 3 rows in efficiently. And with that, you really can't get an overall view of the solder joint, the circularity, the solder fillet. You really can't look at BGAs with visual using a scope with some type of fiber optic input. Next step. Void measurements, that's the key. One of the major keys to the ability to monitor your process. You can look at the percentage of voiding. You look back at that voiding. Most of voiding in BGA happens at the screen printer. Your solder paste integrity. If you open a bucket of solder paste, you plop some in your printer and you go at it in the morning, you'll get some really nice results. As time goes by, somebody might leave the lid off of that solder paste. The factory heats up from a nice cool morning to a later in the day. It gets a little warmer, or in some cases it gets colder in the building. You will have a change in your solder paste consistency, and you might get some contamination in your solder paste. Voiding is also an indication of maybe your substrates weren't clean. You have metallization issues in the substrate. You know, they were shipped and they became corroded to a degree while they were shipped. So the voiding will tell you a lot about your process, but it mostly goes back to the introduction of voids in your solder paste. Essentially, you don't have a void until you apply some heat to the board and run it through the reflow oven. And any impurities and any air or any junk that you may have in the solder joint will, those gases will expand, and that's what creates your voiding. For BGA voiding, you typically can do about 25%. That's about usually the number that most people would consider a good solder joint. If you have less than 25% voiding, in all cases in BGA, you don't want that voiding to penetrate the circumference of the ball. What that does is it gives you some nice edges and will create a vibration crack over time and create issues. So voiding will let you monitor your process pretty efficiently. And as far as voiding on that, one of the processes that you would have is to generate the report. Generating reports are really key to being able to monitor your process from shift, day to day, from shift to shift, or from product run to product run. You know, you put away a dirty stencil and you came back, and ran the product again, and somebody forgot to clean the stencil. So now you have a bunch of opens or you have a bunch of bridging, and that's all based on the fact that your stencil was probably clogged or dirty, things like that. So you can really apply Xray to your process and get some good information. You can also generate the report for later reference, and use it as a learning tool. Okay, next slide. Solder voids in LED assemblies. Solder voids in LED assemblies are the death to an LED. Solder voids are a major problem for LED substrates. You know, the substrate to the LED attachment is critical to remove heat. So if you get a lot of voiding in your LED, you're going to get a lot of warranty returns. And in most cases, if you have a lot of voiding, you just put a $5 bill in each box and call it a day, because it's going to cost you money in the long run. So the X-rays give you the ability to look at those solder defects and fix the problems. Most of the problems with LED is just the basic concept of how they're attached and the power that's applied to them, essentially. You can always tell when someone really doesn't understand LEDs when you buy a flashlight and it has a 2-pound heat sink on a AA flashlight. That's they're trying to pull the heat away because they had no clue how to do it mechanically with the substrate to LED attachment. Okay, next slide. Let's see where we go. Essentially, it's what you're looking at right now, LED inspection. Major flaws in the process and major voiding. Essentially, the LED process is the same in most cases to a BGA inspection. We're looking for excessive solder, lack of solder, and primarily, in this case, voiding. The major difference is we're looking at a square or rectangular pad instead of a BGA pad. So the LED voiding calculations are important, and they use a different criteria than a BGA void would. We're interested in not only the amount of voiding percentage-wise as compared to the pad, but we're looking at the largest void as well as in this case, you can see a lot of extraneous BGA ball, or not BGA, but solder balls underneath the component as well. So there's quite a few different problems with this component as it's mounted. Okay. Another one. Essentially here, we're just looking at voiding, in the attachment. It's pretty straightforward. It's pretty simple. This one we would use a rectangular instead of the BGA ball. Voiding's pretty easy to pick up, but also we can see a lack of solder fillet as well. That's why you've got a nice rectangular outer edge around this component. Doesn't have a real nice solder fill. This could be a solder mask issue, more so than a solder paste issue. Same thing, same concept. I found a new love for the color contrast. Over the years, it was a worthless environment. You would take a nice, back in the day, 256 grayscale image, and you would apply some color to it, and you would bring it down to 32 colors. Pretty much worthless. The new algorithms that we're doing and the ability with computer power as well as monitors, the whole concept, and digital detectors with thousands and thousands of grayscale allow us to do a much better job with color. At one time, PseudoColor was just used to impress the VPs up in the office and to impress the customer to a degree. The advantage of colors and the PseudoColor is that we can tie a color to a specific grayscale value, and it makes for a much faster inspection routine. In this case, we're looking at the solder joint itself in red, and then we're looking at the traces in blue. Following traces in an X-ray is a really tedious task because of the multi-layers. So having the ability to take a layer or a density and assign a color to it and then follow that color makes a lot of sense. If you were training a person that has no concept of X-ray and you tell them that you want to see red in all of the solder joints, that's one way to train an operator pretty quickly. And it works. But in this case, we're applying some other filters, which gives you a contoured effect as well. So it really makes those voids stand out. All right, next one. Automated X-ray. Essentially, in this case, what we're doing is we were looking at an automated X-ray system, which essentially comes in, component comes in, we take an image, we instantly measure the voiding, and then move on to the next part, pass or fail. And that gives us the ability to provide quite a bit of data on the products. The future of X-ray imaging is going to be automated X-ray, where we eliminate the operator's concepts of what is actually a good solder joint and what's not. One of the problems with operators and with manual X-ray is it's all dependent on the person. What they consider a good X-ray, for one, which means the settings of the machine can change drastically. Monitors, you look at a monitor, one person sees a perfect image, other person says, no, it needs a little bit more contrast or it needs less contrast. So there's all these inefficiencies when operators are involved in X-ray. They decide that, there were some medical studies years ago that they took 50 or 100 radiologists and they showed them exact images, and they came up with 50 to 100 different concepts of what that image was, not only was it acceptable or not, but what the outcome for the patient was. And they brought those same radiologists back 2 weeks later, gave them the same images, and even the radiologists couldn't agree on what was a good image and what was not and what was passable. So taking the operator out of the equation is key to getting decent and consistent results to be able to monitor your process. Right, next one.
Hey, Glenn, so we got you to the top of the half an hour, it's 10:30. I know time goes by. Yep. So we can start on BGA inspection next week. But I wanted to open for questions, for about 5 minutes. If people have any questions they want to address now, and of course, they're always welcome to email us or text or tweet, Facebook, LinkedIn, Instagram us. We are, every platform. I'm happy to address. So anyway, I'll open to the floor. You can raise your hand if you have any questions. Otherwise, we'll wrap up the video today and start again with our next Fireside Chat on Wednesday with, again, with Glenn and I in this same Zoom meeting, same time. So sounds like we're going to take questions offline today, Glenn. Thanks again for the great presentation. Thank you all for attending, and I'll see you guys again next week. Thanks so much. Bye-bye.
Thanks. Super cool stuff.
Quay, what you want?